I'm Brandon McKenzie, and in this video, we'll continue to discuss objects, images, focal points, again, all within the scope of diverging systems, but this time we'll be getting more precise. And how do we get more precise in the sciences? Well, we add in math. Now, when we bring math into the sciences, it's typically done through formulas. So the first thing you'll have to learn in order to calculate variables involved in diverging systems is the thin lens formula, which is 1 over f equals 1 over dO plus 1 over di. Now let's take a look at a diagram and see where these terms pop up in a classic diverging system. We'll first tackle what the image distance is. Simply put, it's the distance between the image and the center of the lens. Let's get that out of the way. Next, we'll take a look at the focal length. The focal length is the distance between the focal point and, again, the center of the lens. Finally, the object distance is, you guessed it, the distance between the object and the center of the lens. So once you realize that you're dealing with a diverging system in a question, it's useful to know that the focal length will always be negative. Now, one way you can remember this is that the reflected and refracted rays of light move away from the focal point in diverging systems. Here are two examples of diverging systems doing just that from previous videos. Notice in the diverging lens, we have the rays of light diverging away from the focal point. And in the diverging mirror, we still have the reflected rays moving away from the focal point. Thus, the focal length for both of these systems will be negative. In addition, for diverging systems, the image distance will also always be negative. So what does it mean when an image distance is negative? Primarily, it means that the image is virtual. Now, I want you to recall from previous videos that the term virtual image simply means that the image formed is made by either one or two traced back rays. In other words, the rays of light do not converge to create an image. Also, because these images are made by the tracing back of these rays, that means that the image will always be on the opposite side of either the refracted rays or the reflected rays. Now let's apply what we just learned to a problem. Here we have an object standing 12 centimeters in front of a diverging lens. Recall from previous videos that the object being in front of a lens would indicate that it would be a positive value. We're also told something about the image. The image is formed 2 centimeters from the lens on the same side as the object. Okay, so we're dealing with a diverging system. Thus, the image will always be negative. Plus, the fact that it's on the same side as the object is a good indication that this image will be formed by the back tracings of diverged rays. Thus, it will be virtual, thus it will be negative. Finally, we're looking for our focal length, so let's set that up as f equals question mark. Now, to solve this, we're going to need our thin lens equation. We're going to plug these terms in, and here we have 1 over 12 minus 1 over 2. In other words, 1 over 12 minus 6 over 12, because we got to find that common denominator. Once we work out the arithmetic, we're going to get 1 over f equals negative 5 over 12 centimeters. Now, we're not interested in 1 over f. We want the focal length. Thus, we just want f. We'll get the reciprocal, and the answer here is going to be negative 2.4 centimeters. And if you're curious about what the ray diagram for this system would look like, it looks like so. Notice our object is 12 centimeters in front of the lens, so that will be positive 12. Our image location is negative 2 centimeters. Why is it negative? We see here that it's formed by the back tracing of the diverged ray. Thus, it's virtual and thus it's negative. Finally, our focal point, which is 2.4 centimeters, is negative because the diverged rays move away from it. Let's move on to our next question. Here we have a car that has a side view mirror with a focal length of negative 1. When I read that, I'm thinking this mirror is diverging. Why? Because of that negative sign. And in this diverging mirror, we see a pickup truck that's actually 2.1 meters tall and is 12 meters behind you. Be careful not to mix up these terms. In our thin lens equation, we do not have a term for the size of the object itself. Thus, we will not use 2.1 meters in our thin lens equation. But we do have a spot for our 12 meters, which will be our object distance. Although we do have to be a bit careful here with the nomenclature because the question does say it is 12 meters behind you. So let's pull up a diagram here. When it says 12 meters behind you, Well, that makes sense. That means the truck is behind the car. However, from the perspective of the rearview mirror, the truck being 12 meters behind the car is actually 12 meters in front of the mirror. Thus, the truck will have a positive object distance. Finally, the question asks us, what is the apparent location? In other words, where does the object appear to be? This is a fancy way of asking for the image distance. So let's use our thin lens equation to solve this problem. Now, don't be overly concerned that we're using the thin lens equation to solve a question for a mirror. In actuality, we're using the mirror equation. However, by and large, the two are identical. So you can feel pretty comfortable using the same formula, 1 over f equals 1 over do plus 1 over di for both lenses and mirror systems. When we solve this problem, we have to be sure to isolate for di. So here we go. We'll plug in the values here. And here we have negative 1 over 1 minus 1 over 12. So if you find the common denominator, which is 12, we're going to end up getting negative 13 over 12. And of course, we're not actually interested in what's 1 over di, so we'll find the reciprocal, which will yield negative 12 meters over 13, ultimately yielding negative 0.92 meters. And again, what does that negative term indicate? First, the image is virtual, and second, the image will actually be located behind the mirror. Let's try the second part of this question. In this question, we're asked what is the apparent height of our truck? And now anytime we're asked about apparent height or the size of an object, I want you to think of the magnification equation that you learned in a previous video. Here it is. M equals negative di over do. And from here, we can plug in the terms that we already know. Negative 0.92 from our previous question, and then 12 meters from the question stem itself. When we calculate this, we're going to get the answer of 0.077. Now that we've found m, let's discuss what is m. Now we do know its magnification. It has this ratio here, negative di over do, but perhaps a more intuitive understanding will help us out here. So here it is. Magnification is how much larger the image is compared to the object. In other words, how much is the image magnified when compared to the object. Now when I look at this value here, it's less than 1. So what this tells us is that the image will actually be smaller than the object. This is going to be a minimizing system. Let's now look at the equation. We have hi, image height, is equal to the magnification factor times the original height. So notice again that m is just the factor of how much larger the image is compared to the original object. If we were to plug in our values, we have hi equals 0.077 times 2.1 meters. And if we throw that value into a calculator, we'll get 0.16 meters. And yes, our suspicions were confirmed. Our image is smaller than the object. And this shouldn't be a surprise, because if we look at the focal length here, we have a negative value. Therefore, this mirror will be a diverging mirror. And recall from previous videos, diverging mirrors always produce SUVs, smaller, upright, and virtual images. So now that you've seen a handful of these calculation questions, what you have to do now is practice. And I want you to be very mindful of those sign conventions, because as I said before, and I'll reiterate again, that's typically where students make the most mistakes. But once you get an intuitive sense of the positive and negative signage, these questions become very manageable.